For 2,000 years, an impossible machine lay broken beneath the sea, mistaken for little more than corroded debris. Nothing about the object looked like a computer. It looked like a stone fused with green-black bronze. The object came from a Roman-era shipwreck, loaded with art, luxury goods, and scientific knowledge from the Greek world. Greek sponge divers found the wreck by accident around 1900, beginning the first major underwater archaeological recovery.
The divers raised statues, pottery, coins, and one fragile mass whose real importance remained hidden.
Among spectacular sculptures, the small bronze fragments attracted little attention at first.
Then a crack revealed something no natural rock should contain: a precisely toothed wheel. The lump was not decoration. It was the remains of an intricate mechanical calculator. A single turn could transmit motion through a network of gears and transform time into positions on the sky.
This machine could model astronomical cycles, track calendars, and predict eclipses more than 2,000 years ago. Only about 1/3 of the original mechanism survives, divided today into 82 fragments. The largest fragment preserves the machine's structural core and the most recognizable surviving gear. Understanding it took generations, because corrosion hid the mechanism's internal structure and most of its inscriptions.
Early scholars first called it an astrolabe, a navigation instrument, or a mechanical calendar.
Later, researchers realized the fragments contained a clock-like gear system, far more complex than expected. X-rays made the invisible machinery visible, allowing researchers to count teeth and trace gear trains. Modern computed tomography later uncovered thousands of characters that had remained unread for nearly 2 millennia. The inscriptions were not decoration. They described displays, cycles, and instructions for operating the machine.
The original device was housed in a wooden case, with dials and instructions on both sides. Its power source was simple: a human hand turning a crank. The computation happened mechanically. The gears were bronze, thin, and hand-cut, with triangular teeth rather than modern clock profiles. Every wheel required careful layout, cutting, filing, and fitting with the tools available in the Hellenistic world. The challenge was not merely making gears. It was fitting many calculations into a compact, layered machine.
The surviving fragments suggest a device only about the size of a small box, yet packed with linked cycles. Nested shafts could carry different motions to several pointers, sharing the same central display. The front display combined a calendar ring with the zodiac, turning dates into celestial positions. Set the date, turn the crank, and the entire mechanical sky advances together. The front dial displayed the sun and moon against the calendar and zodiac. A small rotating sphere could show the moon's changing phase as its position shifted relative to the sun. The phase display was a mechanical calculation of the changing angle between the sun and moon. But the moon does not move across the sky at one perfectly constant speed. The mechanism modeled that irregular motion with an ingenious pin and slot system. As the pin moved through the slot, the moon pointer alternately accelerated and decelerated. This translated an ancient theory of the moon's unequal motion into physical bronze. The mechanism also accounted for the slow rotation of the moon's orbital anomaly over several years. On the back, a 5-turn spiral tracked the 19-year metonic cycle. After 19 solar years, the phases of the moon returned to nearly the same calendar dates. The gears converted that long relationship
into a repeatable mechanical calendar.
Original cycles refined the calendar, correcting the small mismatch that accumulates over decades. The back of the mechanism carried two major spirals, one for the calendar and one for eclipses.
The lower spiral tracked the Saros, a cycle that brings similar eclipses back after 223 lunar months. When the pointer reached an inscribed cell, the machine indicated that an eclipse was expected.
The inscriptions distinguished solar from lunar eclipses and encoded details about their expected appearance. Tiny notes could describe timing, direction, and other characteristics associated with an eclipse event. A Saros repeats eclipse geometry, but Earth's rotation shifts where the event is visible. A longer exoligmos cycle helped correct the time of day shift across 3 Saros periods. One hand-powered input coordinated calendars, lunar motion, and eclipse cycles across the entire machine. The mechanism compressed decades of astronomical knowledge into a device that could be explored in minutes.
Its eclipse mathematics drew on long cycles known from Babylonian astronomical observation. Greek mathematicians transformed those cycles into geometry, ratios, and finally, moving machinery. The machine also tracked the 4-year cycle of major Greek athletic festivals.
Its inscriptions name festivals including Olympia, Isthmia, Nemea, and Pythia. For its owner, astronomy, calendars, civic life, and sacred festivals belong to one connected system. The covers carried a technical description of the displays, almost like instructions engraved onto the machine itself. The surviving text describes a front display of the ancient Greek cosmos, including the known planets. But the front mechanism is the most damaged part, so its complete design remains debated. Different reconstructions can fit parts of the evidence, especially where gears and pointers are missing. A successful model must match the physical fragments, the tooth counts, the available space, and the inscriptions. Modern teams have proposed compact planetary gearing that recreates the ancient order of the heavens.
If the reconstruction is broadly correct, the front was a moving mechanical cosmos.
The mechanism reflected the geocentric astronomy of its time, a moving sky organized around Earth. Planetary motion includes apparent reversals, making a complete mechanical display extraordinarily difficult.
Ancient Greek models explained these reversals with combinations of circles moving on circles. A gear system could translate those geometrical circles into the motion of a pointer. X-ray readings preserve long cycle numbers linked by one reconstruction to Venus and Saturn. The known planets were Mercury, Venus, Mars, Jupiter, and Saturn, each with a different repeating pattern. The planetary system had to fit many motions into extremely limited mechanical space. That is why reconstructions are tested not only mathematically, but mechanically. The parts must actually fit and turn. The surviving evidence supports remarkable sophistication, but some details of the original front remain unresolved. The mechanism is both understood and mysterious. Its core functions are clear, while its complete form is still being rebuilt. The mechanism emerged from a Mediterranean world where astronomy, mathematics, engineering, and trade crossed borders. Who designed it remains uncertain, and several centers or intellectual traditions have been proposed. Its maker combined theoretical astronomy with the practical knowledge of a highly skilled bronze workshop. Every gear ratio encoded a numerical relationship between cycles in the sky. The machine appears to combine Babylonian cycles, Greek geometry, and an Egyptian-style calendar ring.
It was not an isolated miracle. It was a synthesis of knowledge accumulated across cultures and centuries.
The device may have served teaching, demonstration, calculation, prestige, or several purposes at once. No surviving text tells us exactly who owned it or how often it was used. Its final journey placed it among valuable cargo moving through the late Hellenistic Mediterranean.
The ship was probably carrying Greek goods toward wealthy Roman markets when disaster struck.
Near the island of Antikythera, the vessel sank and scattered its cargo down a steep underwater slope.
Statues, pottery, coins, timber, and the mechanism entered a cold, corrosive underwater archive. The wooden housing vanished, bronze plates fractured, and corrosion slowly welded gears into mineral masses. Most of the original machine disappeared, leaving researchers to reconstruct a complex whole from scattered remnants. Every modern reconstruction is therefore a negotiation between hard evidence and carefully limited inference.
The goal is not to build the most spectacular machine, but the simplest one that explains the evidence. When a model aligns with the fragments, inscriptions, and mechanics, it becomes a testable historical hypothesis. Working replicas let researchers test whether proposed gear trains can move without jamming or contradiction. A successful reconstruction must reproduce the cycles described by the ancient machine.
Today, computer models and physical replicas work together to explore a computer built without electronics. Nothing else of comparable surviving mechanical complexity appears for many centuries after the Antikythera Mechanism. But the gap does not mean ancient engineering vanished completely. Most machines were recycled, decayed, or never preserved.
Bronze was valuable, wood rotted, and complex instruments were unlikely to survive by chance. The mechanism survived precisely because a shipwreck removed it from the normal cycle of reuse.
It may be the lone survivor of a broader tradition of sophisticated Greek mechanical astronomy.
That possibility changes the question from "how was this possible?" to "how much has been lost?"
New imaging can still recover details from fragments already studied for more than a century.
Each newly read character or tooth count can strengthen one reconstruction and weaken another. The history of the mechanism is also a history of changing scientific interpretation. The machine keeps teaching because its fragments force historians, astronomers, engineers, and classicists to work together. Calling it a computer does not mean it resembled a laptop. It means the device mechanically processed inputs into outputs. A chosen date became a network of calculated astronomical positions and cycle indicators. It belongs to the long history of analog computation, machines that represent quantities through physical motion. The mechanism pushes the history of complex computation much deeper into antiquity. Unlike a static chart, the machine let its user explore changing celestial patterns by turning a handle.
It was a manipulable model, an ancient interface for asking, what happens when? That makes education a plausible purpose. The machine turned difficult celestial cycles into visible motion. It may also have been a prestige object, demonstrating wealth, learning, and technical mastery.
Prediction and calendar planning may have mattered, but the device was probably more than a single-purpose tool.
Without its owner, workshop, or complete front display, some questions may never receive a final answer.
Yet the surviving machine already reveals an astonishing idea. The sky could be calculated with gears. Inside a portable box, ancient engineers compressed generations of astronomy into bronze motion.
Fragments, scans, inscriptions, mathematics, and replicas now work together to reconstruct the lost machine.
Turn the crank, and a date becomes a moon phase, a celestial position, and an eclipse prediction.
Its complexity was not magic. It was the result of observation, mathematics, craftsmanship, and connected cultures.
From Eta 2 fragments, researchers recovered a machine that changed what we thought ancient technology could do. It predicted the sky not by prophecy, but by encoding celestial cycles into ratios of bronze teeth. A small island gave its name to a machine that expanded the known boundaries of the ancient world. The object pulled from the sea was not an impossible computer. It was evidence of a lost mechanical tradition.
And inside that corroded fragment, the ancient sky is still waiting to be read.
The room is new. The conversation is new. Yet for one impossible second, your brain insists this has happened before. That certainty arrives before evidence. You feel recognition, even while knowing you have never entered this place. Déjà vu can feel physical. A pause, a chill, a tightening attention, as if reality briefly slipped out of sequence. You search for the original memory. A dream, a photograph, another room, but the source refuses to appear. Then the feeling collapses. The room becomes ordinary again, leaving only the question of why it felt so certain. The name comes from French, déjà vu, meaning already seen. But the experience is larger than vision alone. People described strangely familiar moments long before neuroscience gave them a modern name. Different cultures have linked the feeling to dreams, spirits, fate, past lives, or moments repeating across time. Science does not require a hidden timeline. It begins with something more ordinary and more mysterious: memory making an error. The central puzzle is simple. How can the brain produce recognition without retrieving anything documentary that was actually remembered? Memory is not one system. A moment can feel familiar, even when you cannot recall where, when, or why. Familiarity is fast and vague. It tells you something has been encountered without reconstructing the encounter itself. You know the face, but not the name. You recognize the street, but cannot remember the visit. Recollection is slower and richer. It rebuilds details, the person, the place, the sequence, and the surrounding story.
In ordinary déjà vu, familiarity surges, while recollection fails to identify a legitimate source.
At the same time, another part of the system knows the present is new. That is what makes the feeling uncanny. Déjà vu is not a full memory replay. Usually there is no precise earlier event you can inspect. It is also different from simply remembering incorrectly. The person often recognizes that the familiarity itself is inappropriate. That awareness may be the key. The eerie sensation could emerge when memory catches its own contradiction. Instead of proving memory is failing completely, déjà vu may reveal that its quality control system is still working. Researchers often look to the medial temporal lobe, a memory network buried deep behind the temples. Structures near the hippocampus help judge familiarity, context, and relationships between parts of an experience. There is probably no single déjà vu switch. The experience may emerge from several memory and monitoring systems interacting. In clinical settings, electrical stimulation of temporal regions has sometimes evoked déjà vu-like experiences. But provoking a feeling does not prove. Every everyday episode begins in exactly the same place. One old idea proposes a tiny processing delay. The same event reaches awareness twice, documentary, making the second arrival feel remembered. Another possibility is a false positive in recognition. The brain's familiarity detector briefly fires for a genuinely new event. Novelty matters because déjà vu contains two judgments at once. This feels known, and this should be new. Recent accounts emphasize that conflict itself, the disagreement between familiarity and novelty, may generate the distinctive feeling. Even this is not a final answer. Déjà vu is probably a family of experiences, with more than one root. One of the strongest experimental clues comes from places that are new in detail, but familiar in structure. A hotel lobby can resemble a childhood school. A new alley can echo the geometry of a street seen years ago. The resemblance may remain below conscious recall. You detect the pattern, but cannot identify the earlier scene. Researchers test this idea with virtual environments, where room layouts can be controlled while surface details change. Participants first explore several scenes without knowing which spatial patterns will return later. Later, they enter new-looking scenes. Sometimes the arrangement secretly matches a scene they can no longer recall. Reports of déjà vu become more likely when the new scene maps onto an unrecalled earlier layout. The trigger does not need an exact copy. A partial structural echo may be enough to create familiarity without identification. That helps explain why déjà vu often feels connected to a place, even when no remembered place comes to mind. Spatial similarity explains some laboratory episodes. It cannot yet explain every spontaneous moment in ordinary life. Déjà vu often carries another illusion, the feeling that you know what will happen in the next few seconds. Experiments can test that confidence by asking people to predict the next turn while they are experiencing déjà vu. The feeling becomes stronger, but prediction accuracy does not reliably improve beyond chance. Your brain may confuse familiarity with foresight. If the moment feels repeated, its ending seems as though it should already be known. After the event, hindsight can make a vague impression feel more precise than it originally was. Memory is reconstructive. It does not replay the past. It rebuilds a useful story from fragments. Déjà vu also increases curiosity. The mind wants to identify the missing source and resolve the contradiction. That search can create false connections, because the brain is exceptionally good at finding patterns, even incomplete ones. This is why past lives, parallel worlds, and precognition can feel persuasive. The experience arrives with certainty before explanation. Science can respect the intensity of the feeling without treating the feeling itself as proof of a hidden reality. Another proposal begins with attention. Perhaps part of a scene is registered briefly before conscious awareness catches up. A fraction of unnoticed perception could make the full experience feel older than it really is. Documentary remembered. Laboratory studies show that previous exposure can influence familiarity even when the original encounter is not consciously remembered. Repeated exposure can make something feel safer or more familiar. But déjà vu includes the extra awareness that familiarity is wrong. An attention lapse might therefore contribute in some cases, without explaining episodes triggered by complex places or thoughts. Many explanations survive because déjà vu is brief, unpredictable, and difficult to capture at the exact moment it occurs. Dreams offer another tempting source. A new scene may resemble a dream whose details were mostly forgotten. But remembering a dream after the event is vulnerable to reconstruction. The present can reshape what you think the dream contained. Déjà rêvé is the specific feeling that the present was previously dreamed. It is related, but not identical, to déjà vu. These overlapping experiences suggest that one label may hide several different memory events. Ordinary déjà vu is widely reported by healthy people. A brief episode by itself is usually not evidence of disease. People describe it during conversations, travel, reading, music, and completely routine moments at home. Some studies find that people who travel more also report more déjà vu, though correlation does not establish the cause. Novel environments may offer more chances for partial resemblance, new details arranged in patterns your memory has seen before. Fatigue, stress, and distraction are often blamed, but their exact role in ordinary déjà vu remains less settled than popular claims suggest. Most ordinary episodes are fleeting. The intensity can be striking even when the experience lasts only seconds. Some people encounter it rarely, others notice it repeatedly. Frequency alone still needs context.
A short, familiar feeling with full awareness is different from an episode that includes confusion, fear, strange smells, or lost time.
When episodes become frequent, prolonged, distressing, or arrive with neurological symptoms, professional evaluation becomes reasonable. The medical connection matters because déjà vu can also occur as part of focal seizures, especially involving temporal memory networks. Neurologists have associated déjà vu-like auras with temporal lobe seizures for more than a century. A seizure-related episode may feel more intense, emotionally charged, dreamlike, or unusually specific than common déjà vu. Yet people cannot always distinguish seizure and non-seizure déjà vu from the feeling alone. Doctors therefore ask about awareness, duration, fear, bodily sensations, smells, sounds, and what happens immediately afterward. Some focal seizures include a rising sensation in the abdomen, sudden fear, unusual odors, or impaired awareness. Electrical stimulation has reproduced déjà vu-like feelings in some patients, linking the experience to specific brain networks. This does not make ordinary déjà vu a miniature seizure. Healthy and clinical experiences can overlap without being identical. Another clinical phenomenon, déjà vécu, can involve persistent conviction that entire events are being relived. Persistent experiences may appear in some neurological or psychiatric conditions and deserve a different explanation and response. The same words can describe very different events. Duration, insight, symptoms, and context determine what the experience means. Jamais vu his contralicistans alla de strangen de transitions, to nefien Kate teen proti de sanctions. Key. Repeating a common word many times can temporarily make its spelling and sound feel unreal. Laboratory repetition can produce jamais vu-like unfamiliarity, revealing that familiarity is actively maintained, not permanently attached. Jamais vu is not simply the exact opposite of déjà vu, but both expose how unstable the feeling of knowing can be. Related experiences can involve sounds, voices, movements, or entire situations, not only things literally seen. Déjà entendu describes something heard as if heard before, while déjà rêvé points specifically toward a remembered dream. Because dreams are fragmented, they can supply countless shapes and emotions that later appear to match real life. Once a match is noticed, the dream may be remembered as more accurate than it originally was. Déjà vu belongs to meta-memory, feelings about memory, rather than the recovered content of memory itself. The brain constantly estimates whether information is known, even when it cannot explain the basis of that estimate. A tip-of-the-tongue state is another example. You know that you know, while the missing word remains inaccessible. These feelings are useful shortcuts. Most of the time, they guide memory efficiently without demanding a complete search. Metacognition adds another layer. The mind evaluates its own confidence, errors, and uncertainty. That self-monitoring may explain why déjà vu feels wrong. At the same time, it feels certain. Scientists can induce déjà vu-like states, but laboratory versions may capture only part of the natural experience. Researchers must often rely on self-report. The participant decides whether the strange feeling truly occurred. Brain imaging is difficult because the episode is brief, unpredictable, and altered by the attempt to observe it. So Prasad Seamley can time resolutionations, the Noexissakantisana generalization, timed limited generalization to the individual differences add more noise. The same prompt may trigger wonder in one person and nothing in another. Best explanation may combine several layers: hidden similarity, familiarity errors, novelty monitoring, attention, and personal context. Déjà vu is memorable precisely because it interrupts ordinary certainty. The contradiction forces attention onto a moment that would otherwise disappear. Surprise and emotion can strengthen the later memory of the episode, even when its original cause remains documentary unknown. Each retelling can simplify the uncertainty. A vague feeling becomes a perfect replay, a coincidence, or a prediction that came true. Online, the strangest stories travel farther than ordinary episodes that lasted 2 seconds and meant nothing. Repetition then makes an explanation familiar. A popular story can feel true simply because you have encountered it many times. There is no scientific evidence that ordinary déjà vu proves past lives, parallel universes, or a timeline line repeating. Modern physics describes strange possibilities, but it does not predict that a brief personal familiarity error reveals another universe. The brain itself is a prediction machine, constantly using past patterns to anticipate what the present should look like. Some researchers suspect interrupted prediction may contribute to déjà vu, but this account is still developing. A compressed pattern from the past may fit the present just well enough to feel familiar, but not well enough to be recalled. Memory was not designed as a perfect archive. It evolved to recognize, predict, and guide action quickly. Déjà vu may be one visible cost of that efficiency, a rare moment when generalization produces the wrong familiarity signal. Yet the mistake is noticed. The brain does not simply accept the new moment as a genuine memory. That may be the least frightening interpretation. The strange feeling could be evidence that your memory system caught its own error. When déjà vu happens, there is usually nothing to solve. The source may never become consciously available. If episodes are frequent, prolonged, or accompanied by altered awareness or unusual sensations, recording the context can help a clinician. A fleeting episode with full awareness is common. A pattern involving lost time, seizures, or persistent distress deserves attention. Science has narrowed the mystery, but it has not reduced every episode to one circuit, trigger, or theory. The most likely answer is not that time repeated. It is that memory, novelty, and awareness briefly disagreed.
Déjà vu feels like a door into another timeline. It may actually be a glimpse of the brain checking the boundary between now and memory.
Around 1200 BC, the Eastern Mediterranean was one of the most connected places on Earth. Kingdoms traded copper, tin, grain, timber, oil, textiles, and luxury goods across hundreds of miles. Bronze made the system possible, but bronze needed both copper and tin was often the harder ingredient to obtain. Palaces did not just rule. They stored food, organized labor, tracked goods, and held entire economies together. Information was part of the infrastructure too. Scribes recorded shipments, taxes, rations, and diplomatic messages. This was an international system where rulers wrote to one another, exchanged gifts, and depended on long-distance stability. It was a world of diplomacy and competition, where peace, trade, and prestige were tightly linked. And that made the entire system powerful, but also dangerously interdependent. Then, within only a few generations, many of these kingdoms and palace centers collapsed or changed beyond recognition. The mystery is not that one city fell. It is that so much of this connected world began failing at once. To understand the collapse, you first have to understand how much everyday life depended on fragile chains of movement and control. A single shipment could carry the metal that armed armies, repaired tools, and signaled wealth across an entire kingdom. Maritime trade was the bloodstream of the Late Bronze Age, especially in the Aegean and Eastern Mediterranean. The chain reaction risk. Food mattered just as much as metal. Palace systems had to collect, store, and redistribute grain to keep labor and authority intact. One major suspect in the collapse is climate stress, especially drought and the harvest failures that can follow it. Paleoclimate evidence suggests parts of the region experienced periods of arids of aridity around the time the system came under pressure. Less rain can mean weaker harvests, tighter rations, higher prices, migration pressure, and political instability. And when food becomes uncertain, the letters from this period start sounding anxious, urgent, and sometimes desperate. One of the clearest windows into the collapse comes from Ugarit, a wealthy port city on the Syrian coast. Ugarit sat at a strategic crossroads, tied into trade networks that connected empires, islands, and coastal states. Its surviving tablets preserve something rare: the written voice of a system under sudden strain. Some letters mention enemy ships, missing support, and threats arriving too fast for help to organize. This is where the famous sea peoples enter the story, though they remain one of the most debated parts of the collapse. Ancient Egyptian records describe groups attacking by land and sea, but they do not solve who every attacker was or why they were moving. They may have included displaced groups, mercenaries, migrants, raiders, or peoples pushed by the same wider stresses hitting everyone else. The deeper problem may have been convergence, several shocks arriving in a system already stretched thin. When one major node in a highly connected network fails, the damage does not stay local. Fewer shipments mean thinner reserves, weaker armies, less authority, and rising pressure on every institution tied to the palace. A drought alone may not destroy an empire, but drought plus war plus supply failure can be devastating. At Ugarit, the crisis appears to have turned into sudden destruction. The surviving letters suggest officials were still trying to respond, even as the situation unraveled around them. Archaeology confirms fire, collapse, and abrupt abandonment at several places connected to the wider crisis. But the collapse was uneven. Not every city fell the same way, and not every region failed at the same moment. Farther north, one of the great powers of the age was also beginning to disappear: the Hittite Empire. The Hittites controlled much of Anatolia and competed directly with Egypt, yet their state also depended on logistics, grain, and loyal provinces. Texts from the era hint at food shortages, political tension, and strained relations across the empire's territory. Large states can look solid on a map, right up until the networks holding them together start to fragment. By the early 12th century BC, Hattusa was abandoned, and the Hittite imperial system had effectively collapsed. This was not just a city destroyed. It was a great power system disappearing from history. Across the water, the Mycenaean palace world of Greece was heading toward its own transformation. Mycenaean power was organized through palaces that managed labor, storage, and administration in ways surprisingly familiar to the East. These tablets reveal bureaucracies tracking goods, workers, weapons, and offerings across the palace economy. That meant warfare, supply, and state administration were tied together. Stress one part, and the whole structure could weaken. Some scholars have proposed earthquake storms as another factor in the collapse of parts of the Aegean world. Earthquakes alone do not explain everything, but they may have damaged already stressed centers or triggered local crises. At Pylos, the last tablets suggest preparations for danger before the palace itself was destroyed by fire. Some records seem to point to defensive mobilization, as if officials expected a Tet attack from the coast. Whether the threat came from raiders, rivals, unrest, or some combination, the palace system was clearly under pressure. Like the East, the Aegean collapse was not one single, synchronized event. It unfolded unevenly across decades. Egypt was one of the few great states that survived. But even Egypt recorded that the age was becoming dangerous. Records from the reign of Ramesses III describe attacks by groups approaching Egypt by land and sea. The famous battle scenes may show Egypt surviving a crisis that destroyed or transformed many of its neighbors. But even here, the attackers were probably not a single nation descending from nowhere. They were part of a wider movement of people through a collapsing world. Some groups were raiders. Some may have been mercenaries. Some were likely families on the move, pushed by scarcity or war. In a world of stressed states, armed outsiders could become soldiers, allies, enemies, or all three at different times. If authorities could no longer feed workers, pay troops, or secure trade, instability could spread from inside as well as outside. By this point, the collapse starts looking less like a mystery-injury invader and more like a web of reinforcing breakdowns. The more connected the world became, the more one shock could amplify another. This is what makes the Bronze Age collapse so modern. It may have been a systems failure. And crucially, not every place met the same fate. Some cities were destroyed, some shrank, some adapted, and some endured. Survival often meant something different from continuity. The old palace order could vanish while communities persisted in new forms. When long-distance systems fail, people do not stop living. They reorganize around what remains possible. Material culture also changed. Bronze remained important, but iron began entering the picture in new ways. Iron did not instantly replace bronze, but in a world where tin routes were unstable, its future potential mattered. The collapse did not simply end one age. It opened the door to a different technological and political landscape. The palace collapse also changed writing. Some bureaucratic scripts disappeared when the institutions that used them disappeared too.
When record systems break, history itself becomes harder to see, which is one reason the end of the Bronze Age can feel so dark.
The world after the collapse was not empty. It was simply less centralized, less palace-driven, and less visibly connected. Some of the seeds of the next age emerged from these surviving coastal networks and adaptive communities. So what actually caused the Bronze Age collapse? The most honest answer is that no single explanation is enough. Climate stress may have weakened food security and made states more vulnerable before other shocks hit. War clearly mattered too. Destruction layers, fortification repairs, and defensive mobilization all point to violence in many areas. But violence itself may have been partly caused by displacement, famine, competition for resources, and collapsing authority. Earthquakes remain more controversial as a master explanation, but seismic damage could have contributed to local crises. The final factor is complexity itself. Highly organized systems can become fragile when too many critical parts depend on one another. This is why scholars increasingly describe the collapse as a cascade rather than a single blow. Different places experience the crisis differently, which is exactly what you would expect in a complex regional collapse. A good explanation has to leave room for variation, because the Bronze Age world did not fail in one uniform pattern. The strongest model is layered. Long-term vulnerabilities made the system brittle. Then multiple short-term shocks pushed different places past their limits. Economic life did not stop. It became more local, more improvised, and often less dependent on distant supply chains. People adapted not just economically, but politically and socially, by reorganizing around smaller, more flexible structures. Recovery was uneven, but exchange networks gradually returned in new forms and along new priorities. In the centuries after the collapse, new maritime players and new cultural forms expanded into the space the old palaces left behind. One of the great long-term outcomes was a world less dependent on palace archives and more open to flexible communication and commerce. The post-collapse world was harsher in many ways, but it also created conditions for new political and technological experiments. This was not the end of civilization. It was the end of one kind of interconnected Bronze Age civilization. That is why the collapse still fascinates people today. It feels ancient, but the pattern is unsettlingly familiar. Complex societies depend on movement, specialization, trust, and resilience. When several of those weaken together, crises can compound quickly. The Bronze Age system rested on four fragile foundations: trade, food, security, and administration. Break one foundation and the system strains. Break several at once, and even major kingdoms can unravel. And this is the heart of the evidence: letters of distress, destruction layers, climate signals, and patterns of regional transformation. No single source says, this is why the Bronze Age ended. The answer has to be reconstructed from many incomplete clues. That uncertainty is part of what makes the Bronze Age collapse feel mysterious. We can see the damage clearly, but not one simple culprit. What disappeared was not humanity, but a particular international order built on palaces, bronze, and long-distance exchange. If you only look for burning cities, you miss the second half of the story: resilience, adaptation, and the birth of a new age. The different world. Some of the time as The Bronze Age collapse was not one disaster. It was a chain reaction across a connected world. Trade made the system rich. Dependence made it fragile. Stress made it unstable, documentary, and multiple shocks made it fail. That is why the story feels so modern, not because the Bronze Age looked like today, but because complexity still cuts both ways. First came connection. Then came overlapping shocks. Then came systemic collapse. Finally came recovery in new forms. The end of the Bronze Age was also the beginning of the Iron Age political landscape that followed. So the question is not simply who destroyed the Bronze Age. The better question is, why was the system so vulnerable when pressure arrived? Because highly organized systems often look strongest just before their hidden weaknesses are exposed. Seen from far enough away, the collapse becomes less a story of one invader and more a story of a world under cumulative pressure. The evidence does not point to a single villain. It points to interaction: climate, war, movement, fragility, and time. That nuanced answer is less dramatic than a single invader story, but it explains much more of what the archaeology actually shows. And in the end, the Bronze Age collapse may be one of history's clearest examples of how interconnected power can fail. It was a world rich in trade, writing, diplomacy, and specialized production, until all of those strengths became liabilities under pressure. What vanished was not life itself, but a high-level system of coordination that had held an entire age together. What replaced it was not simple decline, but a more fragmented landscape out of which new societies emerged. That is why the Bronze Age collapse still matters. It shows how quickly complexity can become vulnerability. It was never only drought, only invasion, or only earthquake. It was the interaction between many forms of stress. The visible disasters were the surface expression of deeper structural weakness below them. In only a few generations, the ancient world reorganized itself into something recognizably different. The Bronze Age did not just collapse, it gave way. And what remains is a warning from deep history. Complex systems can fail gradually, then suddenly. The Bronze Age collapse was the end of an ancient world, but also a lesson in how worlds fall apart. After centralized palaces fell, smaller settlements often became more important than grand and administrative capitals. Collapse did not mean universal extinction. Some institutions survived, and many communities adapted in practical ways. Beneath every ocean, continent, and city, Earth may be storing an astonishing amount of water hundreds of kilometers underground. But this is not a liquid ocean in a cavern. The water is chemically locked inside solid minerals. At these depths, water exists mainly as hydrogen bound into crystal structures, not as free-flowing lakes or seas.
The most important zone lies roughly 410 to 660 kilometers below the surface.
Geologists call it the mantle transition zone, a pressure-built layer between the upper and lower mantle. This hidden reservoir matters because Earth's surface ocean and deep interior are part of one extremely slow water cycle. Water can travel downward with sinking tectonic plates, disappear into minerals, and return through melting and volcanoes. The difficulty is obvious. No drill can reach anywhere close to the transition zone. So scientists investigate this water indirectly, using seismic waves, laboratory pressure experiments, and rare minerals carried upward from depth. Then one tiny diamond inclusion provided the first direct sample from this hidden reservoir. To understand that discovery, first strip Earth into the layers pressure creates beneath our feet. The shallow upper mantle is dominated by olivine, a mineral with relatively limited capacity to store water. As pressure rises with depth, the same chemical ingredients rearrange into denser crystal structures. Near 410 kilometers, olivine transforms into wadsleyite, a mineral that can hold far more water. Wadsleyite does not contain underground droplets. It stores hydrogen inside defects in its crystal lattice. Deeper still, wadsleyite changes into ringwoodite, another high-pressure mineral with major water storage capacity. At about 660 kilometers, ringwoodite breaks down into minerals that generally hold much less water. That sharp drop in storage capacity can force water out and help create tiny amounts of melt. The transition zone may therefore act like a deep sponge, and, at its boundaries, like a water trap. But a mineral's capacity to store water does not prove the entire global layer is filled to that capacity. Because the transition zone is unreachable, scientists read its properties through the way seismic waves travel. Abrupt mineral changes at 410 and 660 kilometers create seismic discontinuities that geophysicists can detect. Seismic tomography converts thousands of travel times into images of faster, slower, colder, and hotter mantle. Their depth, sharpness, and local variations reveal temperature, composition, and possibly the presence of water or melt. Some low-velocity layers near the transition zone boundaries are consistent with small amounts of partial melt. Laboratories test that interpretation by recreating deep Earth pressures and temperatures in diamond anvil cells. When hydrous ringwoodite transforms under lower mantle conditions, experiments can produce melt between the new mineral grains.
Seismic observations beneath North America found velocity drops where mantle flow models also predicted downward movement across 660 kilometers.
Together, experiments and seismic data support dehydration melting as one way water may remain trapped near the transition zone. Still, seismic signals and experiments were indirect. Scientists needed a piece of the deep mantle itself. The crucial sample came from a rough diamond recovered near Juína, Brazil. Deep source eruptions had carried the diamond upward fast enough to preserve a mineral formed hundreds of kilometers below. Inside the diamond was a microscopic inclusion, too small to see without specialized instruments. X-ray diffraction identified the inclusion as ringwoodite, the mineral expected in the lower part of the transition zone. It was the first reported terrestrial occurrence of this high-pressure olivine polymine polymorph in a natural sample. Infrared spectroscopy showed that the inclusion was water-rich, in the mineralogical sense. It contained substantial hydroxyl. The preserved inclusion indicated roughly 1 weight% water locally within the transition zone mineral. That was direct evidence that at least part of the transition zone is hydrous, not proof that the whole layer is equally wet. The diamond solved one question and sharpened another. How representative was that tiny piece of deep Earth? A speck inside a diamond had transformed the debate from pure theory into direct observation. The discovery was widely described as an ocean in ocean inside Earth, but that phrase can be deeply misleading. The mineral stores water as hydroxyl, hydrogen bonded within the crystal, not liquid water filling open space. Hydrogen can substitute into defects where